one thing I think viewers should appreciate is all of this is being built on top of the kind of distributed ledger technology that, Bitcoin, Ethereum, et cetera. And I think one of the main purposes or functions of that technology is to create, this shared state that's verifiable by all parties and in theory, fully decentralized without requiring third parties to also do those verifications. But I think what you and your team are working on is kind of this next advancement that allows some key progress around privacy, scalability, handling computational complexity. So I'd like to kind of break down all those elements for our audience, because this is a very technical, and I tend to be technical. I'm sure you do too, and I don't want to lose anybody. So first of all, can we talk a little bit about why are blockchains kind of transparent? Why can you trace transactions all the way back to Genesis on Bitcoin, for example?
Right. Well, I mean, you can trace them because they're public, and they have to be public to be ratified, as you know. So if we're looking at sort of what the what we might call the layer one project is, so the core blockchain project, that is to provide a kind of an economic record of events that is agreed upon by anyone who chooses to come online and validate what's gone on in that blockchain. So, as you say, very unlike the sort of the deep vaults of data that banks retain that are only validated internally inside that bank and therefore cannot be admitted to public code. No one can go and program the assets on a bank's balance sheet. All this is done in the open air. That obviously brings privacy concerns. That was one of the things that, for example, Aztec was addressing. But it brings also huge scalability problems, because if I say I want assets to be born digital, wrapped in a programmable machine, so in other words, they can be admitted to code bases written by anyone in the world, I need to know that the data set that I'm operating on is actually the moving of the asset and is not just a secondary record of what happened to that asset. And that's what makes blockchains really magical. But it doesn't take much imagination to see that if you wanted to even put, let's say, just Visa scale transactions through blockchains, no single node, no small node running somewhere could possibly process all of those transactions, particularly at surge capacity. And for Web3 adoption, we're counting on many, many times the number of transactions, thousands, maybe millions of times the number of transactions that have ever passed through the Visa network. So this is where we've also got this scaling problem. And that's where zero knowledge proofs, and we should maybe spend a little bit of time on where these zero knowledge proofs in cryptography came from. But that's where these zero knowledge proofs and what we call these layer 2 networks, which is where largely they operate, come to the rescue. They are able to make it provable that maybe millions of transactions over a short space of time happened and were executed entirely correctly, so with all the kind of the security that we would want for our assets, but the cost of checking them is trivially cheap. And this is a kind of magic that the science of this area only started 40 years ago, and really it's been the sort of the Web3 era that has moved this from a science where it was proving that these things were possible, but they were not particularly performant, and has turned them into sort of industrial grade pieces of mathematical machinery.
Wow, that's a great summary. And, to focus on the LM1s for a short moment, when they were first devised, many of these mathematical techniques kind of weren't even fully formed. I mean, it also has been driven, the math and the science, the computer science behind this, by this movement into Web3. And this transparency on the layer ones was required for essentially final settlement, for verifying that you don't have the double spend problem, that all assets are accounted for at all times. And it's kind of this mutually agreed upon place that anybody can verify. But now we're getting to the point where the volume of transactions that we're asking for is going to scale exponentially. And with it, that computational complexity. And so we need to take some, I hate to use the word shortcuts, but we need to be more efficient with our computational processes such that we can handle that, but not give up any of the properties the assurances that we've come to expect with these transparent layer ones. So I think it's good. I'm glad you brought up the history. I'd like to dive a little bit into this history in cryptography and how it's evolved until now, and why you think this is the correct time to kind of implement it, and how that might be a necessary prerequisite for really scaling Ethereum and other L1s up to the millions of transactions you alluded to.
Sure. So I mean, the last maybe I'd say 8 years of development in this cryptography, it started actually with privacy. So it was I'll say Zcash. I normally say Zcash. That's the language difference. But Zcash were the people who really first spent time taking zero knowledge proofs onto a blockchain. Of course, they were doing it for what optically to you and I would look like quite different reasons. So it wasn't for scaling reasons, it was for privacy reasons. It was what you alluded to, everyone could see every transaction, and that's obviously, by the way, the problem that my old company Aztec addresses as well, and they're sort of really the leaders on Ethereum for doing that. But if we go right the way back to the 1980s, when it was really sort of 3 MIT professors who are now all sort of these very illustrious sort of gods of Web3, but at the time they were trying to address another kind of scaling problem. So they had noticed that I don't know whether you've come across this, but your listeners may not have done. There's a thing called the 4-color theorem, and the 4-color theorem says if you imagine any map of any arrangement of countries you can imagine, not just in this world, but in any world, you can always color this thing with 4 colors. And this was kind of known to be true, but no one had ever been able to prove it. And they proved it was true for 5 colors, but it's a stronger thing to say you can do this always with 4 colors. And when I say with 4 colors, I mean no 2 countries which are adjoining share the same color. And so you can always do any map in 4 colors. And the first proof of this was a fake proof in the 1890s. And then a real proof came from some Scandinavian mathematicians who said, yeah, this thing's true. Trouble is, the proof runs to, I can't remember how many pages, sort of hundreds and hundreds, if not up to thousands of pages. And they'd reduced down every possible theoretical map into 1,000 configurations, and then it had to be checked by a mainframe computer. Well, not really a proof, and this scared mathematicians. They thought, we're now starting to, it's a bit like a blockchain approving transactions. The mathematical community was saying this doesn't scale, because if we have to work through 1,000 pages of machine-like working every time we want to check something's true, mathematics can't securely scale. We don't know when someone says that they prove something that it's true, and this is a real problem. So this is where the zero knowledge proof arose from, and it was people like Macaulay and Goldwasser who were working on this in the 80s. So fast forward, to 2014, and the Zcash demo, I think, there have been various clusters of technologists who had observed this before, but the thing that allows you to say, is a computation, has it been done correctly, and allows you to kind of prove this to someone with a tiny, tiny amount of information and very little work required on their side to check that it's true. That is both a scaling property and a privacy property, because both of these things require me to leave information at the door, and I just send you a little proof and you can check it, right? So you can see how privacy, which is the act of me not showing you all the information, and scaling, which is the act of I can show it's true without having to show you the information, are really 2 sides of the same coin. And you can see, therefore, why these zero knowledge proofs, which were originally devised for scaling, then used early on blockchains for privacy, and now we're using them really for both. And maybe the best analogy that I've heard, and it is not mine, and I think it's probably a hand-me-down analogy, but it's a very good one, is what is the zero knowledge proof trying to achieve? It's saying, I as the spender of some money on a public blockchain, I'm prepared to engage in a huge amount of work so that I can save you, the verifier, and you are the blockchain, most of the work required to know it's true. And a good example is where's, I think in the US you call it where's Waldo, we call it where's Wally. And the classic analogy is I have a picture of a where's Waldo, and I want to show to you that I know where Waldo is. but I don't want to leak any of the information that allows you to establish where he is. I just want to prove this fact to you. And so I take a sheet, I drill a little hole in the sheet that is Waldo shaped, and I put the sheet over the top of this picture of where's Waldo. And so I've now been able to prove to you, you can see Waldo, but you can't see the context. You can't see any of the workings that it took to find Waldo. And therefore, all your work is still ahead of you if you want to go and find Waldo. I've saved you all of your verification cost. I've actually hidden Waldo, so that's kind of the zero knowledge bit. I've hidden where he is, and yet I've shown you that I know that I have this knowledge. And that's really how zero knowledge proofs enable us to scale blockchains. They allow computation off-chain to prove something that has been correctly executed with absolute certainty, but often they can not reveal all the information, or they can just choose to leave it at the door because it's too much to load the blockchain with.
I think that's a borderline miracle kind of mathematics. It's as radically fundamental to our progress in this space as Satoshi was solving the Byzantine generals problem. This is a key necessary component for us to really get onto that next level where we're going to deliver on the promises of Web3. As you know, with the current state of things, there's a lot of skepticism that Web3 could deliver, decentralized finance or many of the promises of that it has always given us. I believe strongly that zero knowledge proofs and these other kind of technologies that allow for scalabilities, they're going to be what get us there. And I assume that you do too, given that that's where most of your life's work is at this point. So given this, what practical applications now in the kind of, let's focus on Ethereum, but in Ethereum, is the main practical application right now scaling to L2s? Or is it other types of kind of zero knowledge verifications? Let's talk about maybe DeFi. But what do you see are those practical applications?
Yes, if you want sort of crudely, these proofs can separate into two kinds. One is the sort of what you might call the universal type. So I can kind of prove anything, but it might not be particularly optimal for the case that I'm using. But that's a very good proof system to use for kind of general purpose layer twos, right? So if, for example, the thing that I want to do is I want to go and build a layer two, I want it to be completely secure. I want Ethereum to be able to check everything that goes on inside it. But the things happening on that network are going to be very multifarious. So they might be an Aave transaction over here, a MakerDAO transaction over here, sending some USDC to someone using an escrow account. The universal proving system is good for that because it can allow proofs that any computation are correct, and you can use that same proof over and over and over again to kind of reduce down the cost of checking that stuff. On the other hand, there are maybe more complex types of statements you might want to make where a bespoke proof that has sort of been hand sewn for that particular application. So one thing, for example, we built at Geometry is a thing called mental poker. It's basically a shuffle argument. It allows secure private shuffling of cards. And actually, we've got a blog on our website explaining how that works, written by one of our cryptographers, Nico Mumblat. So there are often times when you have a specific thing that you want to do, and you want to do it either with privacy, or usually with privacy than scalability, or you want to kind of take some trust assumptions out of the mix. It might be things like shuffling through validators, or all sorts of things you might want to do on blockchains, and zero knowledge proofs will enable you to do that. I mean, one very good example where we're all going to need ZKPs is in gaming and virtual settings. So, for example, if we want to enter strategy games and we don't want to reveal all the private information associated with a character that we're playing, that's a very good example of where the strategy and how interesting the strategy in a game is might be completely defeated unless there are private traits, strength features or whatever they might be, hidden inside that asset that are only revealed in the context of battle or some sort of engagement with another character. In that instance, you can use zero knowledge proofs, and you can use another sort of related concept known as MPC, so that you can prove that the strength of this character is greater than the strength of this character, whatever it might be. Or another example would be, my bank balance is greater than some amount X, but I don't want you to know the amount X. Or it might be, I want to prove to you just online that I'm over 18 and I've got some signed digitized version of my passport. Well, instead of giving you my date of birth, which is a bit of a risk for me, I can give you a range proof that just says whatever the date of my birth is bigger than some number. And that proves, or I should say lower than some number, and that proves that I am therefore over 18. But of course, even things like that, they leak a bit of data, because if I told you, let's say when I was 20 years old, that I was over 18, fast forward, I don't mind saying I'm 35, you now know that I'm more than 33. I mean, you can tell that from the video anyway, but if we were just exchanging online, you could now tell that I'm over 33. So there's a lot of context involved in these privacy techniques as well. And often there's going to be an amazing new sort of contextual science probably around how to extract information or how to protect information with zero knowledge proofs, because they're private, but only up to the point that you understand what context you're giving off.
And is it a fair or a true statement to say that use of this technology does not require sort of a trusted computing environment, like that typically one would have to in a centralized situation to keep this data leakage or revealing the underlying data? Is that a true statement? And because I think that's a key component for people watching to understand is this is for a decentralized or distributed set of interactions between various parties. Is that fair?
That's exactly right. And by the way, there is a cost to this, so there's a penalty. It's nothing comes free in the universe, and we pay a moral price for this. So let's suppose that we are right, that geometry is right to assume that all code in Web3 is going to be run through zero knowledge proofs, right? So every time now you execute some code, you've got, yes, great cheapness in the verification of the code, but you've got a massive blow up in the cost of producing and executing that code, this thing called proof construction. So this is basically this is the moral payment, right? I get very cheap verification that doesn't imperil the decentralization of the network, but I have this huge blow up in my compute cost. And this needs to be tackled somehow, and we are very likely going to become heavily reliant on hardware. We built specific hardware to speed the execution of games and graphics that we now all depend on our devices. Our suspicion is we're going to require also a piece of a little silicon chip, a little accelerator sitting natively in all devices that is there to execute the code that you want to send to blockchain. So if Web3 is going to be ubiquitous, these chips are going to be everywhere. And that's another sort of part, to your point about building hardware. This is another part of the infrastructure we think is going to be pretty critical.
And I assume then that that burden, that computational burden, is borne by whomever is initiating the transaction in the first place. In other words, it's done once and it's computationally heavy, but it doesn't multiply to all other actors on the network. The zero knowledge proofs would essentially take care of that aspect of it. So it just, I think it shifts the responsibility kind of from the centralized actor, this intermediator in the traditional sense, and it shifts it towards the edge, towards the individual kind of submitting their transaction for validity. Is that true?
That's right. You can't, and you can't fake proof. So anyone, there are, before anyone writes a zero knowledge protocol or a new paper, they have to prove that it has these soundness properties. Where and the point being that if someone could, that there are a lot of arguments that are run to prove these security features, but if someone could fake a proof, this will be fatal. There is actually a fascinating rescue story. I actually interviewed on this channel Zuko Wilcox of Zcash, who gives a great account of just such a rescue story where there was a soundness proof, but there was an error in the proving system that was at one point deployed into Zcash, and it was actually the now chief scientist of Aztec, who was previously one of the lead technologists at Zcash, who managed to discover that there was a way of faking proofs. And so theoretically, an attacker, it would have to have been an incredibly cryptographically literate attacker. So it would have to have been a very brilliant person who found it. But but they could have spent an infinite amount of money. So that was an attack vector that I think it lasted for at least 9 months, because they had to wait for the next natural time to upgrade the entire network in order to deploy the fix. And so, yeah, you've got to be very sure that your zero knowledge proof system. So, I mean, the funny thing about Zcash is we still don't know if there was an attack. We may never know if there was an attack. We suspect strongly that there wasn't, and that the only team that really could have found that vulnerability was the Zcash team themselves. But it'll never be known. It'll never be proven. There's this kind of weird ontology that there is some truth in the universe about this blockchain, which no one on the planet will ever know for sure, which is a very, very strange thought, except the attacker, of course, if there was an attacker. So, yeah, they have these strange properties, these zero-knowledge proofs.
That's very interesting to think about.
Hey visionaries, thank you for tuning in. For more free crypto content like this, head over to realvision.com/crypto. You'll get early access to the most brilliant minds in the space to cut through the noise, get in-depth analysis, and get you ahead of the curve with unbiased insights.